This video was made about a trip that I made out to the South Pacific in 1956 when I was working for the Naval Radiation Laboratory in Hunters Point, California, San Francisco. Start out with some of the fundamentals with some of the large atoms in nature like U-235 are greatly unstable because of the neutrons and protons in the nucleus. They can actually split apart, and when they do so, they produce neutrons. Now, other materials like plutonium can be induced to fission, like when you hit them with a neutron, they break apart and they produce excess of neutrons that can then go to fission or break up other plutonium atoms. When that happens, there's a release of energy as the two particles or more fission particles are produced. So you can get a chain reaction when there's excess neutrons, more than two, about average 2.5 per nucleus. The energy release is absolutely enormous and factors about 10 million times a regular high explosive detonation. And as a release of radiation as well, and gamma rays and X-rays. This type of energy is called renewable energy. It's like wind, geothermal, biomass energy, or solar energy, because you can produce uranium and other heavy elements in the fission process, and you have leftover materials. For example, as renewable energy, you can take the energy that's produced in the form of heat and use it to heat water, as shown here, and then the water can be heated hot enough so it becomes steam, and the steam can then be used to turn a steam turbine and produce power or electricity. On the other hand, if all of the energy is released at one time, then you get a huge explosion, and this is the essence behind making an atomic or a hydrogen bomb. If you take a little gun and have a uranium-235 plugged down at the end and shoot it into a bunch of uranium, then you can get it to fission, because the excess neutrons from the little plug make the slug at the end become greater than critical. On the other hand, if you put the material in the center and have some high explosives around the outside, you can implode it, and the compression then forces the uranium all together and makes it go critical and gives you a huge explosion. The difficulty is you have to do it uniformly and detonate the high explosives, as you see in this little cartoon drawing showing how the Fat Boy worked. You have high explosives around the inside, outside, and compress it to the inside and force it in and implode. Here's a picture of the little boy, which was a gun type where you have a rifle barrel and shoot the slug down and make the weapon go off by causing instantaneous fission in the nuclear slug at the end. Here's the other type called a Fat Boy, which was named after Churchill, supposedly by Freeman Dyson. Thin Man was named after Roosevelt by Dyson. So the rumor goes around physicists. The Thin Man was the one that was dropped on Hiroshima, and the Fat Boy was the one dropped on Nagasaki. They're each about 20 kilotons of normal high explosives, and they each killed around 75,000 people. Edward Teller then got the idea that if you could make things fission, why can't you take things like deuterium and tritium, this is just heavy hydrogen, force it together to form helium, and then get a huge amount of energy out of that reaction. This is basically what's going on in the sun when you're forcing hydrogen together to produce helium. And the helium then is released with a bunch of energy, which keeps the sun burning. And the hydrogen core is gradually being converted into helium until the sun, the outward pressure of the light is not enough to sustain the gravity from imploding. The star then implodes and produces a nova or a supernova, depending on its size. But then Teller's idea was, why can't we do this with an atomic weapon? You have to get the hydrogen up to a temperature of about 10 million degrees. 5 or 10 million degrees is what you find at the center of the sun. So the idea is to implode a atomic bomb and get it to implode the hydrogen to have a fusion reaction. You're fusing things together. Here are some things from the initial tests in Nevada. Actually, the first one that we have here is from Crossroads Baker. It's called Bikini Baker. It's an airdrop of 8 kilotons, a little less than that at Hiroshima. But you can see the devastation to the fleet. A lot of Japanese ships and old outclassed American ships. But on the right-hand side, you see one being sucked up the spout, and then another one to the left of the spout. This is a smaller test in Nevada. These are called continental tests, or CONUS, C-O-N-U-S test. These were smaller ones in the earlier days. And then they wanted to see what it was like to be troops here. Not a good idea, but they did have them far enough away, and I looked up some of the radiation doses that the troops got here, and they were not that high, but I don't know about the fallout that came out, where it went. Here's a picture of an atomic artillery shell that was shot and exploded. I don't know how successful these are nowadays. I think they're quite advanced and they can make fairly small ones. Next, we see a photograph of a very early detonation, somewhat in the microseconds, I would guess, by the picture of it. You see how unsymmetrical it is at the bottom. That's what happens in a dirty bomb. It squirts out the ends. This one's not too bad. It's fairly uniform. This is the laboratory where I worked, USNRDL, Naval Radiological Defense Laboratory in Hunters Point. 7 stories high and no windows, and it was supposed to be able to survive an atomic blast. Not a direct one. From there, I went up to Travis Air Force Base and flew from Travis out into the Pacific. And our first stop was going to be the Hawaiian Islands. This was all MATS, Military Air Transport Service. We went out to Oahu and stayed in Fort DeRussy, which is right up by Waikiki. We were going to go out later that night. Well, we didn't get out for about 2.5 days. We just hung around waiting for a good plane to go out. They'd always seem to be sprouting oil or something. The next stop was Kwajalein Island out in Marshall Islands. There were fierce battles over this island in World War II. Several thousand Japanese died. The reason was, you see right there, the U.S. wanted the island for the airstrips. In the Marshall Islands, I was located on Perry Island and assigned to a ship called the YAG 39. This gives you a perspective of where the Marshall Islands are, pretty much out there next to nothing except other small islands. Here you see in the upper left side Eniwetok, and then you go pretty much to the direct east, and there's Bikini. And I was on Eniwetok, and a lot of the tests were out at Bikini. Here's a picture of the Eniwetok Atoll, and you see Perry Island right down there in the lower right-hand corner, about 4 o'clock. And some of the tests were on the islands close to us, the littler tests, where they had 8 KTs. Here's a satellite image showing Perry Island. We were on the bottom left-hand side at about 6 o'clock, is where we had some of our electronics labs. I was aboard this YAG 39. There is a picture of it going under the Golden Gate Bridge. In the bow, we had a laboratory. We were supposed to be covered by 20 feet of water, and we'd go out and do figure-8 fallout patterns in the figure-8 fallout patterns in the fallout range. Here's a list of all of the nuclear tests were listed from 1945 to 1962. Linus Pauling, the chemist, Nobel Prize winning chemist, was instrumental in getting the tests to stop because they were finding carbon, cobalt, and other radioactive materials in all parts of the world and in the food chain. And of course, it concentrates to higher and higher levels as you go on the food chain. So milk would have a lot of cobalt in it. Basic type of shots that we had out in the Pacific were underwater, surface, or tower shots, and air burst. And they were at different locations in Eniwetok and Bikini atolls. I didn't get out there until sometime in June, so I think first ones I saw were probably Flathead or Blackfoot. The little ones, they tell us at night there's going to be a drop in the morning or something, and open up your windows and doors. Huge shockwave would come through the barracks. Here's an airdrop from a B-29. This one looks like it's on a chute, and it looks like it's one of the gun type. Here's one of the early shots, 3.8 megatons, which is an enormous blast. You have about a 2-mile radius that goes up to around 10 million degrees, 5 million degrees. It's devastating. That's called Cherokee. That's the first shot there. I wasn't there. Aboard the Yag, we'd get to stay out until the airdrop or surface blast went off. We could look at it through dark glasses. You'd face away from it, then turn back into it, and the glasses were so dark I couldn't find the sun at high noon in the South Pacific. But you'd see this awesome cloud come up over the horizon. It was surrounded by something called a stellar glow. It would be undulating a purple glow rising up, and you could see it. We were usually about 75 miles away, we were told, and we saw some of the really big ones come off. This is Zuni. I didn't get to see that one. Redwing Erie, this is 14.5 kilotons. That was probably on one of the islands relatively close to us. We didn't take part in the smaller ones. We just took part in the larger ones, and where we would be able to go do figure eights in the fallout pattern. Here's Blackfoot, 8 KT. That was smaller. That's probably more like what they were wanted for artillery shells. The next one coming up here is Dakota, and this is an underwater burst, and I've seen the videos of this, and you just see a wall of water about 3 times the height of that ship come over, and the ship disappears, and then the camera disappears, but they did retrieve the film from it. This is another picture of Dakota at a later time, and you can see how awesome they look, and that's the only word I can think to describe them. They're awesome. As a young man and young physicist out there, I was thoroughly impressed by how wicked they are. Anyone who sees one of these go off will never want to do anything like start a nuclear war. It's just awesome. The next shot down here is Apache, fairly big one, 8 July. I'm sure I did see this one, and we did do fallout patterns in them, but I don't remember the particular shot, which one was which, that is. Then we have Tiwa, and I'm sure I saw this one too. This is one of the biggest ones. Now these numbers don't jive with what we recorded. I think they were, some of these bigger ones were 20 megaton weapons. The next shot is a shot of a filter that we sent up with just some kind of inert grease on it, and we'd have it on an elevator to go up. We'd do figure eights in the pattern and collect the fallout. It comes down, and we'd collect them at first about every 30 seconds, then every minute, then every 2 minutes, 5 minutes, and 10 minutes, etc., and pattern them that way. The fallout particles were then thin sectioned by a geologist, so you could see how well the radiation was mixed in with a solidified material. So it was a bomb casing and sand, and anything else that went up there. This was recorded by one of my friends, Carl Miller, and unfortunately I don't know which shot it is, but it does demonstrate the full effect of a nuclear weapon going off. And here's one of the last shots it went off, and you see an inversion layer up on top. That's when the cloud goes up and hits a warmer air or colder air and spreads out horizontally before it punctures through. This is one of the earlier shots in Redwing, the ones I participated in. And after you went out on one of these missions, you got a little certificate that said you took part in. This is mine. It says that I took part in Operation Redwing, 1956, out in the Pacific. When we came back, we spent about a year or 2 years analyzing the data. People were afraid that World War III would start and that it would be the end of the world. I was convinced after seeing those go off that nobody would ever be crazy enough to start a nuclear war. It would be horrific. Finally, underground testing and above ground testing was stopped in 1962 because fallout was found all over the world. They knew how to build them by then, and different types of style of trigger mechanisms. And the computer models were quite good enough. From there, we went to mutually assured destruction, MAD, and each side had enough weapons to make sure that there was no winner or loser. Then they went to MERS, multiple independent reentry vehicle systems. Each vehicle had multiple warheads, and they had 15-minute strikes planned. First one, second one, third one. The subs would come up the second and third and launch their attacks, and they targeted down to the top 200 cities in population in each one of the countries. So a place like Prescott would have its own 3 targets. What's going to happen? Well, depends on whether we are beyond the technological adolescence and what happens to the fanatics if they get a hold of one. Would they try and set it off? Some of them would without realizing the consequences. And it would mean, I believe, utter destruction of the country where those missiles came from or where the weapons came from. That was Hiroshima, and I think this one is Nagasaki after the 20 kiloton weapons went off. This was destruction for about 1 or 2 miles across. You can rebuild, but it takes a time. This is Hiroshima after, 60, 70 years? 50, 60 years, or I guess this photo was taken. I'm sure there's still radioactive materials on the ground, but the level of radioactivity is low enough so that it's not any threat to long-term survivors who have been there, kids who have grown up around it. That's about all I have to say. It was a very interesting time of my life, and if anybody knows anyone who wants to start a nuclear war, hey, take them out and show them some of these pictures. Tell them it's awesome. You don't want to do it or think about it. If that was the end of my presentation, but let's hope that it's not the end of everything. I don't think so. I have a lot of faith in mankind and that there are intelligent beings here on Earth.